We often navigate our world vertically, moving from one floor to another, maybe taking an elevator, an escalator, or, yeah, more commonly, stairs and ramps. But have you ever truly paused to consider the intricate thought that goes into making these seemingly simple connectors work for us? It's this whole realm of meticulous design, precise engineering, and critical safety regulations that we just glide over every single day without, a second thought.
What's truly fascinating here is that while we might completely take them for granted, these everyday elements are absolutely fundamental to how we experience and move through any multi-level structure. They dictate flow, accessibility, and surprisingly, even the very character of a building. It's quite profound when you stop and think about it.
Today we're taking a deep dive into the surprisingly complex world of stairs and ramps. Our mission for this deep dive is to extract the most important nuggets of knowledge from our sources, exploring everything from their basic components and diverse types to the meticulous calculations that ensure they're safe, efficient, and crucially, universally accessible. Get ready for some genuine aha moments about the very ground you walk on. And just for context, this deep dive is based on some specialized architectural and construction documents detailing design principles and practical applications of stairs and ramps. So when we think about vertical movement in buildings, it feels intuitive, right? Moving up and down. But what are the core drivers behind why architects choose one method over another? How do stairs and ramps stack up against, say, an elevator or escalator?
Yeah, that's a really important question right at the outset. Providing efficient and safe vertical access is, well, it's a foundational requirement for any multi-story building. It has to work. Stairs, ramps, elevators, and escalators each play a distinct, often complementary role in connecting different floor levels. That could be within the structure itself or even on its exterior, like fire escapes or entrance ramps. They all serve that fundamental need for efficient and safe vertical circulation, but how they're deployed, their strategic deployment, is far from arbitrary.
And there's a general rule of thumb for how these are strategically deployed, isn't there? It's not just a free-for-all, let's put an escalator here kind of choice.
That's absolutely right. There's a typical guideline, yeah. It suggests that stairs and ramps are often primarily used in buildings that are, say, 3 stories in height and less. The rationale behind that is kind of multifaceted. For a lower number of floors, the physical exertion for most users is generally quite manageable. People don't typically mind taking a flight or 2, maybe 3. And crucially, stairs and ramps are also significantly more cost-effective. Think about the initial construction costs, but also the long-term maintenance compared to complex mechanical systems like elevators or escalators. They don't require power in the same way. They're inherently robust.
Okay, so that makes sense for lower buildings. Simpler, cheaper, less effort required.
Yeah.
So if you're going higher than that, maybe 4 floors or more, that's when you start seeing elevators and escalators really dominating the scene. What's the fundamental shift in thinking there? Is it just the sheer number of floors, or is there more to it?
Yeah. Oh, it's definitely more than just the floor count. Elevators and escalators are employed on buildings of 4 floors, or more precisely because they are designed to handle far greater vertical distances, sure, but also much higher volumes of traffic, and critically, with significantly less physical effort from the users. Imagine the sheer impracticality or even the physical strain of asking office workers or maybe hotel guests to walk up 5-10 flights of stairs multiple times a day. It's simply not efficient or practical for the vast majority of people in a busy commercial or public setting. These mechanical systems, they dramatically improve the speed and the ease of vertical movement, which becomes absolutely critical in taller, high-occupancy structures where time and convenience are really paramount.
Okay, but here's where it gets really interesting and honestly a bit counterintuitive for me. You mentioned a fascinating exception to this rule, specifically with shopping centers. Even if they only have 2 or maybe 3 main levels, they frequently opt for escalators over stairs. Why is that? It's clearly not just about the number of floors then.
This is a perfect, almost brilliant example of how very specific functional requirements can completely override those general guidelines we just talked about. It's context dependent. In buildings such as shopping centers, which often have quite high floor-to-floor dimensions, think about those big, airy mall spaces, and they absolutely must accommodate an immense number of people moving around. Well, Escalators are the common, preferred, and strategically vital choice. The rationale here isn't solely about the number of floors. It's deeply rooted in the unique environment and, maybe more critically, the economic goals of a retail space. See, escalators are designed to maintain a continuous, predictable, and effortless flow of customers. People just step on, they're carried up or down, they don't have to pause, choose a direction, or exert themselves much at all. This maintains what some call a shopping mindset. Their brains are kind of freed up to focus entirely on the retail environment around them.
Ah, so they're not thinking about the effort of climbing, but rather looking at the shops flashing by. It's almost like creating a near hypnotic retail experience.
Exactly. This continuous, easy movement maximizes the visibility of storefronts as customers are constantly moving past them. Compare that to being confined in a narrow stairwell, or maybe waiting around for an elevator, or even worse, having to make a conscious decision like, okay, am I going to bother going up to the next floor? Escalators remove that decision point.
So it's not just about convenience then. It's almost a subtle psychological and economic strategy at play. Stairs or even elevators could inadvertently create bottlenecks, break that seamless flow, and make the shopping experience feel less frictionless, maybe even tiring. It's fundamental to the retail choreography.
Precisely. Escalators prevent those bottlenecks, which could deter customers or make the experience feel less efficient, more effortful. In a retail environment, any perceived friction in the customer journey can potentially have a direct negative impact on sales. It sounds crude, but it's true. Escalators are engineered for these high-traffic retail environments, ensuring that a very large number of people can move smoothly and continuously between levels. This directly contributes to customer comfort, sustained engagement, and, ultimately the bottom line. It's about optimizing that whole customer journey and preventing anything that might pull them out of that browsing or purchasing mindset.
Okay, so from those very deliberate choices about how we move vertically, let's unpack the design of stairs themselves. A stair isn't just a series of steps you kind of throw together. What's the core philosophy behind designing one that truly works, that feels right?
Right. If we connect this to the bigger picture, the design of stairs is it's a deeply delicate balance between human factors, how our bodies work, and the overarching architectural intent. The primary goal, as our sources emphasize, is to place the least amount of physical strain on the people who use them. hmm This speaks directly to ergonomics, fitting the design to the human body, and also the profound principles of universal access. It means thinking meticulously about things like consistent step heights, that's crucial, adequate tread depth so your foot fits comfortably, and comfortably graspable handrails. These elements aren't just about ticking boxes for minimum code compliance. They are really about ensuring user comfort, safety, and accessibility for the broadest possible range of individuals. Think about a child, an elderly person, someone carrying bags, or someone with a temporary mobility challenge. But simultaneously, a stair must reinforce the design character of the space and structure of the building. So it becomes an integral, often a leading part of the aesthetic. It can be a sculptural element, a grand statement piece, or a very discrete necessity. Its design always communicates something about the space it inhabits.
That makes incredible sense. So it's doing two jobs at once, being easy and safe to use, but also being a significant design statement. How do things like the material choices, the stairs form, its proportions, how do they contribute to this character? I mean, I can picture a grand sweeping staircase in a public building having a very different impact than, say, a minimalist utilitarian one in an industrial setting.
Absolutely. The choice of material, for instance, significantly influences the feel and character of a stair. Our sources point to the common materials being wood, steel, or concrete. Wood, well, it has that inherent warmth, the grain patterns, remarkable versatility. It's often associated with traditional appeal, craftsmanship, and a welcoming, maybe even cozy atmosphere. You see it a lot in residential settings. Its construction might involve cut stringers, where the profile of the steps is actually visible on the side, kind of celebrating the stairs form. Or you might have housed stringers, where the treads and risers are precisely mortised into the stringers, showcasing traditional joinery and giving a more finished, solid aesthetic. A wooden stair can really evoke a sense of home or history or intimate craftsmanship.
Okay, wood feels warm and traditional. And what about steel and concrete? How do they differ in their character and typical applications? And what defines their construction?
Right. Steel offers immense strength and rigidity, which allows for much thinner, more delicate, and often quite open profiles. Think airy, floating steps sometimes. This creates a remarkably modern, sleek, or even industrial aesthetic. It's frequently seen in commercial spaces, industrial settings, or contemporary residential designs where maybe a minimalist, exposed structure is desired. Its fabrication often involves precise welding and bolting, which speaks to its robust structural properties and allows for large, unsupported spans sometimes. Concrete, on the other hand, is known for its incredible durability, its inherent fire resistance, that's a big one, its mass, and excellent sound dampening capabilities. It feels solid. It's often used in large commercial buildings, institutional settings like universities or hospitals, or outdoor settings. It conveys a sense of permanence, unyielding solidity, maybe even a monumental presence. Construction usually involves building meticulously crafted formwork, the mold placing steel rebar reinforcement inside for tensile strength, and then pouring the concrete in place, or sometimes using precast elements made off-site. So you can really see how the material choice fundamentally dictates the vibe. A rustic, warm wooden stair, a sharp, precise steel one, or a monumental, unyielding concrete one. Each tells its own story about the building.
Beyond the aesthetics and the comfort, though, there are some pretty strict rules governing stairs, aren't there? It's not just about making them look good or feel right. This seems like an area where safety takes absolute precedence.
That is a critical and absolutely non-negotiable point. The design and construction of every single stair must meet a number of stringent building codes and, increasingly, comprehensive universal design standards. These codes are paramount for public safety. Fundamentally, they're there to prevent falls, ensure the structure holds up, and critically guarantee adequate egress, a safe way out in emergencies, like during a fire. They also explicitly mandate accessibility for people with disabilities, specifying things like precise ramp slopes, which we'll get to, continuous handrail requirements, even minimum widths for clear passage. Universal design, while related to codes, actually goes a step further than minimum legal compliance. It aims to ensure maximum usability and dignity for the widest possible range of people, proactively anticipating diverse needs and making the built environment truly inclusive from the ground up, not just as an afterthought or add-on.
So what are the real-world consequences if these codes aren't met? It sounds like it goes far beyond just, a slap on the wrist or a fine.
Oh, the consequences can be devastating, frankly. They impact everyone involved. There can be significant legal liabilities for property owners, architects, builders, ranging from hefty fines to potentially crippling lawsuits if injuries occur. Then there are the immediate and tangible safety hazards for users, potentially leading to severe falls, injuries, or even, in tragic cases, fatalities. And critically, failing to meet accessibility codes can render a building unusable or at least highly challenging for certain populations. This can lead to significant, costly, and disruptive retrofitting expenses later on, or even, in extreme cases, forcing a building to be partially or entirely closed down until it complies. It's not just about avoiding fines, it's about fundamental human safety, dignity, and legal responsibility.
And speaking of projects involving stairs, I imagine interior designers typically deal with them in two main ways. What are those usually, and what are the distinct challenges of each approach?
Yeah, broadly speaking, interior design projects involving stairs usually fall into one of two categories. Either the design and construction of an entirely new stair, or the remodeling and upgrading of an existing one. Designing a new stair means integrating it seamlessly into a new building's plans right from the earliest stages. You're considering everything from its structural support, how it connects, its finishes, and how it aligns with the overall architectural and functional vision of the new space. It's part of the initial concept. Remodeling an existing stair, on the other hand, is a very common necessity, especially in older buildings, and it presents a really distinct set of complexities and challenges.
Yeah, I can totally visualize that. You might have a truly beautiful, maybe historic building, perhaps with a grand original staircase. But those stairs, while charming, could be incredibly dangerous by today's standards. Maybe they're too steep, no proper handrails, the balusters are too far apart. It seems like a real design dilemma.
Exactly that scenario. Remodeling is often undertaken precisely to upgrade a stair in an older building to meet the current, often much stricter, building codes and accessibility standards. And this can be an incredibly complex design and construction challenge because you're working within an existing, often quite rigid structure. You can't just knock everything down easily. The goal is often to preserve as much of the original charming character as possible while simultaneously bringing critical elements like the step heights, the tread depths, the handrail grip, the baluster spacing, bringing all those up to modern safety and accessibility standards. It often requires really creative engineering engineering and design solutions to achieve compliance without entirely demolishing the historical integrity or the aesthetic of the original structure. It's a delicate dance between preservation and modernization, and it demands immense skill and sensitivity.
All right, let's really get into the nitty-gritty now. If we're going to truly understand stairs, we need to speak their language, know the parts. Some of these terms you might already know, but I bet others will give you a whole new appreciation for the precision involved in every single ascent and descent.
This is definitely where we begin to see the incredible detail and specificity that goes into architectural design and construction. Each of these components has a critical, often code-governed role, and many are subject to specific rules or controls for safety and performance. They aren't just arbitrary labels, they represent essential functions and safety features.
Okay, let's start with those small vertical pieces that run alongside the stair, the ones supporting the handrail. What are those called, and what's their main job?
Right. Those are called balusters. They are the vertical components that specifically hold the handrail in place. Their crucial safety role is that these are precisely spaced to prevent people, especially small children, from falling through the open areas of the railing. This is why baluster spacing is rigorously governed by building codes. For instance, a very common international requirement is that no gap between balusters should be large enough for a 4-inch sphere about 100 millimeters to pack through. This seemingly small detail is a vital safety measure, specifically designed to protect infants and toddlers from accidental falls or becoming entrapped.
Okay, balusters support the handrail and fill the gaps. So, distinct from that, there's also something called a guardrail. How does that differ, and where will we typically find one?
Yeah, a guardrail is fundamentally different in its primary purpose from balusters on a stair run. It is a protective rail that is used on landings or on any open floor levels, specifically to prevent people from falling between floor levels or off an edge. Its purpose is to protect those open edges where there's a significant drop-off thing around a stairwell opening on an upper floor, or on a landing where the stairs aren't immediately adjacent, or maybe on a balcony edge. It ensures safety where there are no steps immediately adjacent. It's primarily about preventing a fall from a height off an open edge rather than preventing someone from slipping between the gaps on a stair run itself. Different primary function.
Got it. And then there's the handrail itself. We all grasp it. But what are the key things to know about its design and the code requirements surrounding it?
The handrail, this is the continuous section of railing, typically running parallel and adjacent to a stair run, designed specifically for a person to grasp as an aid when ascending or descending. We stress the aid aspect because it provides vital balance, support, and stability. This is especially important for those with mobility issues, or in an emergency situation, or, frankly, just to prevent a simple stumble for anyone. Building codes closely control multiple aspects of handrails. Things like whether the railing is required on one or both sides of the stair. Often both are needed for wider stairs. Its precise height above the nosing of the treads, usually within a narrow range for an ergonomic grip. Its continuous graspability, meaning no breaks or obstructions that would force a user to let go mid-climb or descent. Codes also often require specific extensions at the top and bottom of the stair run. These extensions provide continued support for users as they transition off or onto the stairs, and they often require a return curving back to a wall or a newel post to prevent clothing or bags from snagging, which could cause a fall.
Okay, moving up quite literally. What is headroom in stair design, and why is that so critical? Sounds obvious, but I imagine the specifics matter.
Yes, headroom is the minimum clear vertical distance. It's measured from the edge or the nose of any tread straight up to any part of an obstruction directly above it that could be a ceiling, a structural beam, or the underside of the landing above. This is absolutely vital for user safety and comfort as it directly prevents head injuries. You definitely don't want to bump your head. Typical code requirements often mandate a minimum of 6 feet 8 inches, or about 2.03 meters, of clear vertical space throughout the entire path of travel on the stair. It's a fundamental aspect of creating a usable and safe passage, avoiding any nasty bumps.
Right, and when you have a longer stair, there's often that flat section in the middle or maybe the top or bottom. That's a landing, correct? What's its role?
Yes, exactly. A landing is the floor or platform found at the very beginning or end of a stair, or, more commonly, strategically placed between two or more stair runs. It serves multiple crucial functions. Firstly, it's a necessary resting point, especially on longer flights. Secondly, it's a place to safely and comfortably change direction in the stair's path, like in an L-shape or U-shaped stair. And thirdly, it's a critical safety feature. For example, landings are often legally required by code after a certain maximum number of risers in a single flight, typically somewhere around 12 to 16 steps, depending on the code. This provides users a natural break, reduces the perceived exertion, and significantly reduces the potential severity of a fall if someone were to lose their footing on a very long, uninterrupted flight of steps.
Then there's often a more substantial post, usually at the start or end of the stair, kind of anchoring the handrail. What's that called? And does it serve more than just a structural purpose?
That's the newel post, or simply newel. The newel is the terminating baluster, typically larger and more robust, found at the bottom or top of a stair run. While it serves as a strong, vital anchor point for the handrail, providing structural stability, it's also very frequently a significant decorative element. Its design, its material, maybe ornamentation like carving or a cap. These can profoundly set the tone for the entire stair's aesthetic. It often serves as a visual punctuation mark and defines the initial impression of the staircase, especially at the bottom.
And a subtle but, you mentioned, incredibly important part of the tread itself is the nosing. What is its specific purpose? Why is it so vital for safety and comfort? It seems like such a small detail.
The nosing is that part of the tread that slightly overhangs the riser below it. It might only be an inch or so, maybe less. It's a seemingly minor detail, but it's remarkably critical from an ergonomic standpoint. Its primary purpose is to reduce the problem of a person accidentally kicking the face of the riser as they ascend the stair, especially if they have larger feet. This subtle overhang provides just that little bit more usable foot space on each step, making climbing feel more comfortable and natural by allowing the ball of the foot to find a secure purchase. It significantly reduces the risk of tripping over the riser edge. Without nosing, a stair would feel much more abrupt, less forgiving, and more prone to stumbles and falls, particularly on descent.
Okay, now for some of the overall measurements. What is the rise of an entire stair, as distinct from an individual step's riser height?
Right. The rise refers to the total vertical distance that is traveled on an entire staircase. It is the perpendicular measurement taken directly from the finished floor level at the bottom to the finished floor level at the top. And mathematically, it is precisely the sum of all the individual riser heights added together. So if you're going from the ground floor to the second floor, the rise is that entire vertical climb that the staircase facilitates, say 3.3 meters in our earlier example.
Got it. And then the riser itself, that's the individual vertical bit.
Yes, the riser is the vertical part of a single step, the upright component positioned between two successive treads. This defines the height of each individual step. And I can't stress this enough. It is absolutely crucial that consistent riser heights are maintained throughout an entire staircase from the very first step to the very last. Even a seemingly small variation in riser height, perhaps as little as a quarter inch or 5-6 millimeter, can profoundly disrupt the person's natural gait and rhythm, causing them to stumble or lose their footing because your body expects consistency. This consistency is paramount for safety, especially for people who rely on muscle memory for movement, like those with visual impairments or simply anyone moving quickly.
And the part you actually step on, the horizontal surface, that's the tread.
Yeah, right. Correct. The tread is the horizontal part of a stair, the flat surface that your foot bears down upon when ascending or descending. Its depth is just as important ergonomically as the riser's height, and its material considerations are vital for safety. You want adequate depth to comfortably fit most of your foot without feeling cramped or like your heel is hanging off too much. And the surface needs to provide good slip resistance, especially in potentially wet conditions or high traffic areas where wear could make it smooth.
Okay, and the overall horizontal measurement of the stair, the total length it takes up on the floor plan, that's the run.
Exactly. The run is the total horizontal depth or projection of an entire stair. It is calculated as the sum of all the individual tread depths added together, excluding the final landing area. It represents the overall horizontal footprint or length that the staircase occupies in a building plan. This dimension is critical for space planning, making sure the stair fits within its allocated architectural space. It's directly related to the total number of treads and the depth chosen for each tread.
And finally, the structural backbone of the stair. What holds all these pieces, the treads, the risers, together?
That would typically be the stringer. The stringer is the primary structural support element for the stair treads and risers. It's sometimes also referred to as a carriage or maybe a house stringer, depending on the construction style. These are the inclined beams running alongside or underneath the steps. This component plays the fundamental, often unseen role in holding the entire stair together structurally, carrying the loads from people walking on it down to the supporting structure. Its aesthetic can vary significantly. It might be left exposed, maybe made of steel or heavy timber, on a more utilitarian or industrial stair, celebrating that raw structure. Or, more commonly in finished spaces, it's completely hidden with various finishes like drywall or wood paneling on more decorative, refined stairs. So its appearance, exposed or hidden, profoundly affects the overall look and feel of the design.
And then there's an interesting type of tread that gets used in specific situations, often when turning a corner without a landing, called a winder. Tell us about those. I think you mentioned earlier they're often restricted in certain building types.
Yes, a winder is a unique kind of wedge-shaped tread used specifically in a turn-of-the-stairway run. Unlike a landing, which provides a flat rectangular platform for turning, winders allow the stair to make a turn using individual tapering steps. They fan out from the inside corner. You'll find these primarily in residential work, especially older homes or light spaces, because they are highly space efficient. They allow a stair to make a 90 or 180-degree turn in a much smaller footprint than would be needed for a landing. However, and this is crucial, commercial building codes almost universally severely restrict or outright prohibit the use of winders in means of egress or public access stairs.
Why the restriction in commercial buildings? That seems like a pretty significant safety concern if they're still commonly found in homes. What's the issue?
It is indeed a significant safety concern, and that's precisely why the restriction exists for public and commercial settings where traffic is higher and user familiarity might be lower. The primary reason is that winders inherently have a constantly varying tread depth. They are very narrow at the inner edge of the turn, where the steps pivot, and they progressively widen towards the outer edge. This inconsistent tread depth makes the step less stable and far more unpredictable underfoot, particularly at that narrow inner part where you might naturally place your foot when turning tightly. This poses a significant hazard, especially in high-traffic environments where people are moving quickly, maybe carrying things, or crucially, during emergency egress when clear, consistent, predictable steps are absolutely paramount for rapid and safe evacuation. Furthermore, they present substantial challenges for individuals with certain mobility impairments who rely heavily on consistent step dimensions and a stable surface for safe navigation. In commercial or public spaces, the priority is always on maximizing safety and universal usability for the broadest possible population. Consistent rectangular treads provide that predictability in a way that winders simply cannot, hence the restrictions.
Okay, that makes sense. Now that we've got a handle on the individual parts, let's zoom out and look at the whole structure. Stairs aren't just one shape. They come in all sorts of configurations.
Right.
Each with its own kind of character, purpose, and maybe even unique challenges in design or use.
Absolutely. If we connect this back to the bigger picture, the choice of stair type is far from arbitrary. It's never just picked randomly. It's a complex decision dictated by a multitude of factors. Things like the available space, that's often a huge driver, the building's specific function, is it a home, an office, a public monument, the desired traffic flow patterns and the volume of people expected to use it, and, of course, the overarching architectural style that the stair needs to complement or even define. Each type really optimizes for different needs and creates a distinct user experience and visual impact.
Let's start with maybe the most straightforward one, the simplest configuration.
Yeah, that would be the straight run stair. It's pretty much precisely what it sounds like. A single, uninterrupted line of steps providing the most direct path possible between two levels. While it definitely requires a long, linear space to accommodate its full length, it can eat up floor area. Its simplicity makes it incredibly efficient for direct vertical travel and very easy and intuitive to navigate. You often see them in industrial settings, fire escapes, or sometimes in very modern minimalist homes where that directness is part of the aesthetic.
Okay, simple and direct. And then we have designs that start to introduce turns, presumably to make them more spatially efficient.
Exactly. Next up is the L-shaped stair. This configuration features a single landing, usually square or rectangular, positioned at a 90-degree turn somewhere along the flight. This layout is significantly more compact horizontally than a straight run because it effectively folds the stair back on itself, making it a highly popular and practical choice in many residential settings where space planning is key. Plus, that landing provides a natural resting point and a safe, comfortable area to change direction, breaking up the continuous climb and offering a moment of pause, which can feel more gracious.
Similar to that, but with a full 180-degree turn back on itself, is the U-shape.
Right. The U-shaped stair consists of two parallel runs of steps connected by a single, often quite generous, landing that spans between them, forming a full 180-degree turn. This design is exceptionally efficient for vertical travel within a relatively compact footprint, often fitting neatly within a defined stairwell space. It can also create a very grand and welcoming feel, especially if the landing is spacious. It's commonly found in both residential settings, like a traditional center hall colonial, and smaller commercial buildings, allowing for efficient circulation and often creating an impressive architectural statement in a central hall or foyer.
We just discussed them as individual steps, those wedge-shaped ones, but there's also the winder stair as a distinct type overall, right?
Yeah.
Using those steps to make the turn.
Yes, exactly. The winder stair, as a type, directly utilizes those wedge-shaped treads we just talked about, allowing the stair to smoothly turn, usually 90 or 180 degrees, without the need for a flat landing area. As we noted, its highly space-saving nature means it's found primarily in residential work, particularly where maximizing usable floor space is a top priority, or in older buildings where space was tight. But again, because of those inherent safety concerns related to the inconsistent tread depths, especially at the narrow end, commercial building codes very strictly restrict or outright prohibit these in public access areas or main escape routes. Their application is really limited primarily to private, low-traffic spaces.
Okay. Now, for something a bit more grand, maybe something designed to create a real sense of arrival or elegance, you often see curved stair. What defines that?
Ah, yes, the curved stair. This type features a graceful, sweeping arc, often designed without a central newel post or the very tight geometry of a spiral. They flow more gently. These are often seen as the epitome of architectural grandeur and elegance. They're frequently used for impressive entrances or significant design features in public buildings, historical landmarks, high-end hotels, or luxurious residences. They create a profound sense of fluidity, movement, and sophistication. However, their undeniable beauty comes with significant practical challenges. They are notoriously complex to design accurately and even more complex to build due to their nonlinear, often unique geometry. Every step can be slightly different. They require intricate calculations for each unique tread and riser and highly skilled craftsmanship, particularly in wood or custom metal work for their construction. This often makes them very expensive compared to other types.
And finally, for the absolute maximum in space efficiency, perhaps where other types just won't fit, there's the spiral stair.
The spiral stair is indeed the most compact option available. It's characterized by treads radiating outwards from a single central column or pole. It is extremely space efficient, making it an ideal choice for situations where usable floor space is at an absolute premium. Think accessing a small loft, a secondary access point to a basement or deck, or sometimes used as a dramatic sculptural element in a very tight corner. However, that extreme compactness comes with usability trade-offs. They can be quite challenging and often feel uncomfortable or even precarious to navigate, especially when carrying large items. You have to twist as you climb. And they present significant accessibility challenges for many people. Their tight turns and the varying tread depths, narrow near the pole, wider at the outside, mean they are rarely suitable or permitted as a primary means of egress in public or commercial settings. They're often chosen more for their striking visual appeal and undeniable space-saving ability than for their everyday practicality or comfort as a main stair.
Wow. Okay, this is where it gets truly fascinating for me. It's not just about the aesthetics or the general shapes we just discussed. There's some serious, precise math involved behind the scenes to make sure stairs actually work correctly and are safe for everyday use. It's surprisingly specific, and honestly, it sounds like quite a design puzzle to solve.
Knowledge is most valuable when understood and applied, right? And this is a perfect example of that. These computations are absolutely fundamental. They're not just suggestions. They're critical to ensuring a stair is not only compliant with those stringent building codes we talked about, but also comfortable, ergonomic, and efficient for actual human movement. It's a really critical aspect of applied design where even seemingly small errors in calculation can have significant, sometimes genuinely dangerous consequences for the people using the stair. Let's maybe try to walk through an example almost as if we were the architects ourselves facing a typical scenario. We've got a specific floor-to-floor height to cover, a defined stairwell space, length and width, and we need to make a safe, functional, and reasonably comfortable stair fit within those constraints.
Okay, yeah, let's do that. So let's set the scene with some typical parameters, maybe like the ones provided in our sources. Let's say we have a floor-to-floor height of 3.3 meters. The available stairwell length is 4.3 meters, and the stairwell depth, or width, is 2 meters. Where do we even begin this architectural puzzle? How do you start?
Right. The very first step, typically, is to make an assumption about the individual riser height. This is often the starting point because it's so critical for comfort and heavily regulated by codes. In this example calculation from our source, they assume a riser height of 150 millimeters, which is 0.15 meters. Why start here? Well, riser height is a key ergonomic factor. Building codes usually specify a very narrow acceptable range, often somewhere between 4 inches and maybe 7.75 inches, which is roughly 100 millimeters to 197 millimeters. Too high is tiring, too low feels awkward. So picking a comfortable height within that range, like 150 millimeters, about 6 inches, is a good starting point. It's a balance.
Okay, so we've assumed a riser height of 0.15 meters.
Mm.
Once we have that target, how do we figure out exactly how many individual steps up we actually need to cover that total 3.30 meter vertical distance?
Good question. The next step is to compute the total number of risers required. This is a simple but absolutely crucial division. You take the total floor-to-floor height and divide it by your assumed height for each individual riser. So in our example, 3.3 meters total height divided by 9.15 meters assumed riser height gives us exactly 22 risers. This calculation tells you precisely how many individual vertical lifts are needed to get from one floor to the next using steps of that assumed height. Now, in real-world practice, you might get a number with a decimal, like 22.3. Since you can't have a fraction of a riser, you typically round up to the nearest whole number, say 23 risers, and then recalculate the exact riser height by dividing the total height, 3.3 meters, by the new number of risers, 23. This ensures every single riser is precisely the same height, which is critical for safety. But for this example, 22 works out perfectly.
Okay, so 22 risers. Does that mean we then have 22 horizontal steps, the treads we step on? I remember you saying this is where it gets confusing for many people.
You've hit on that common point of confusion again. No, it does not mean double 2 treads. To compute the total number of treads, the rule is always take the total number of risers and subtract 1. So in our case, 22 risers minus 1 equals 21 treads. Why the minus 1? Think about it. The very first step up requires a riser, right? But the final step up you take lands you onto the next floor level or onto the landing itself. That floor or landing is the final walking surface. There isn't another tread after the last riser. You step onto the destination, not onto one last extra tread. It's a subtle but absolutely vital distinction for getting the calculation right.
Okay, that makes perfect sense when you visualize it like that. The floor is the last tread. Now, most stairs covering that height would likely have a landing somewhere in the middle, right?
Yeah.
To break up the run, especially if it's a U-shape fitting into that 2-meter depth. How do we figure out how many treads are on each part of the stair run, say, before and after the landing?
Exactly. For a height like 3.3 meters, a landing is almost certainly required by code and definitely desirable for comfort. So let's assume it's a standard U-shaped stair with 2 equal runs and 1 landing in the middle, fitting within that 2-meter depth. We have 21 total treads to distribute. The source material calculation suggests we compute the number of tread steps per run, or per landing, meaning leading up to it. If we have 21 total treads, and the landing effectively takes the place of one potential tread position in the sequence, or we simply divide the treads between the 2 runs, the calculation shown in the source, 21, then 2, yields 10 steps per run. So 10 treads leading up to landing and 10 treads continuing after the landing. This step is all about distributing those 21 total treads across the individual flights, effectively defining the precise horizontal length of each segment of the staircase leading to and from the landing.
Okay, 10 treads per run. And the landing itself needs to have a specific dimension, doesn't it? It needs to be wide enough for people to turn comfortably and meet code requirements. How do we calculate that?
Yes, the landing dimensions are critical. To compute the dimension of the landing, specifically its depth, how far it extends along the direction of travel, we often use the available stairwell depth or width. In our example, the stairwell depth is given as 2 meters. For a typical U-shaped stair where the landing spans this full depth between the 2 parallel runs, we might divide this by 2 if the landing only occupies half the depth to allow passage beside it. Or in this case, the calculation seems to imply the landing itself is 1 meter deep. Let's assume the landing is 1 meter deep based on the source calculation 2 meter 2 equals 1 meter. This calculation determines the necessary clear depth of the landing. It must provide adequate space for resting, safely turning 180 degrees, and it often must meet minimum code dimensions. Codes frequently require the landing depth to be at least as wide as the stair itself, and often a minimum depth like 36 to 48 inches, roughly 0.9 meters to 1.2 meters, depending on local regulations. So 1 meter seems reasonable here. It's both a safety and convenience measure.
Right, so we have the number of risers, 22, the number of treads, 21 total, 10 per run, and the landing depth, 1 meter. Now, the final piece of the puzzle for the steps themselves. The depth of each individual tread, the horizontal part we actually step on. How is that calculated, given all these other dimensions we figured out?
Okay, now we bring it all together to compute the depth of each individual tread. We use the total available stairwell length, 4.30 meters. From this total length, we first need to subtract the horizontal space taken up by the landing at the turn, which we calculated as 1 meter deep. That leaves us with the horizontal distance available for the treads themselves in one run. Then we divide that remaining horizontal distance by the number of treads in that run, which we determined was 10. So the calculation is 4.30 meters total length, 1 meter for the landing depth, divided by 10 treads per run. That equals 3.30 meters divided by 10, which gives us 0.33 meters or 330 millimeters for the depth of each individual tread. This is the horizontal dimension of the part you step on. And getting this right is profoundly critical for safety and comfort. 0.33 meters, about 13 inches, is a generous depth, allowing the entire foot to comfortably rest on the step, preventing slips, and ensuring a natural, consistent walking rhythm that minimizes the chance of a misstep. Codes usually have minimum tread depth requirements too, often around 10 or 11 inches, 254, 280 millimeters.
Wow. Okay. And our sources also mention a visual aid for this computation, showing a grid diagram with landing marked and the steps numbered, maybe 1 through 11 for the first run and a 12 through 22 for the second run, counting the landing transition. How does seeing it drawn out like that help us understand the practical layout of all these numbers we just crunched?
That kind of diagram is invaluable, honestly. It's essential for truly visualizing the practical application of all these meticulous numbers we just calculated. It clearly illustrates how the landing acts as the pivot point, dividing the overall vertical climb, the top two risers, into two distinct segments or runs. You can visually trace the path. The first run of 10 treads leading to riser 11, then the flat, critical 1 meter deep landing, and then the second run of 10 treads from riser 12 up to riser 22, which lands you on the next floor. It takes those abstract calculations, the 22 risers, the 21 treads, the 1 meter landing depth, the 0.33 meter tread depth, and makes them tangible. It shows the precise flow of steps and the exact placement of the landing within the 4.30 meter by 2 meter stairwell footprint in a practical, real-world stair layout. It profoundly reinforces how each calculation directly translates to the physical dimensions and the precise arrangement of the staircase, showcasing the architects' and engineers' careful planning to make it all fit and function safely.
Okay, we've covered the meticulous design thinking, the specific parts, the different types, and even the precise math behind stairs. But how do these complex calculations and sometimes beautiful designs actually get built on site? I have to imagine a delicate wooden stair is constructed very differently from a massive concrete one or a sleek steel structure. The reality of building must dictate so much.
Indeed it does. The choice of material fundamentally dictates the entire construction methodology, the sequence of work, the skills required, everything. Each material, wood, concrete, steel, presents a unique set of challenges and opportunities. They differ in terms of structural support needs, the required tools and equipment, the finishing processes involved, and even the overall impact on the construction timeline. Understanding these practical differences isn't just academic, it's absolutely key to appreciating the finished product you walk on and the skilled labor involved in bringing that design off the paper and into the real world.
Let's start with wood, maybe the most traditional material for stairs, especially in homes. What's the typical methodology there? What kind of craftsmanship is involved?
Right. For wooden stair construction, the methodology primarily focuses on the careful assembly of various pre-cut or site-cut wooden components. It often involves traditional carpentry and joinery skills, which can be quite intricate. This typically involves cutting and precisely positioning the stringers, those inclined supports. As we mentioned, these can be cut stringers, where the profile follows the rise and run and is often left exposed, showcasing the structure. Or they can be housed stringers, where the treads and risers are carefully notched or mortised into the side of the stringer itself, concealing the connection points for a cleaner, more finished appearance. The risers, the vertical parts, and treads, the horizontal parts you step on, are then meticulously attached to these stringers. This uses various joinery techniques, maybe dowels or complex joints, along with mechanical fasteners like nails or screws, and often construction adhesive for added stability and, importantly, to prevent annoying squeaks later on. Wooden stairs can vary immensely in complexity, from very simple utilitarian designs to highly ornate traditional structures with intricate balusters, newel posts, and handrail volutes. They're often constructed primarily on-site by skilled carpenters who cut and fit each piece custom to the specific dimensions and angles of the space, although some components, like pre-assembled railing sections, can be prefabricated. The final stages involve careful sanding to get a smooth finish, and then staining or painting to achieve the desired aesthetic look and provide protection, bringing out the warmth and natural beauty of the wood grain. The timeline is generally quite flexible, allowing for on-site adjustments as needed.
Okay, wood involves cutting, joining, finishing. It feels quite crafted. Now, what about concrete stairs? They seem so monolithic and permanent. How are they built, given their weight and the nature of the material?
Concrete stair construction is fundamentally a wet process, and it's quite different. It typically begins with the meticulous and highly precise building of formwork. This formwork is essentially a sturdy, temporary mold, usually custom built on site from wood panels like plywood, or sometimes specialized steel form systems. This mold defines the exact three-dimensional shape of the finished stair, including the treads, the risers, the landings, and any integrated structural stringers or slabs. Creating accurate formwork is a critical skill in itself. Before any concrete is poured, steel reinforcing bars, or rebar, are carefully placed and securely tied together within the formwork according to engineering drawings. This reinforcement mesh is absolutely critical because it provides the necessary tensile strength, the ability to resist pulling forces which concrete inherently lacks on its own. This allows the finished stair to resist bending forces and support the loads placed on it. Once the rebar cage is correctly positioned, the concrete mix is poured into the forms. It's often vibrated using special tools to remove any trapped air bubbles and ensure the concrete fully encases the rebar and fills every corner of the mold, creating a dense, strong structure. Then comes the curing process. The concrete needs to be allowed to harden and gain strength, which can take days or even weeks depending on the specific concrete mix, the size of the pour, and environmental conditions like temperature and humidity. This curing period is crucial for achieving the concrete's full design strength and durability. After the concrete has cured sufficiently, the formwork is carefully stripped away or removed, revealing the raw concrete stair structure. Subsequent finishing often involves troweling the surfaces while the concrete is still partially wet to get a smooth finish, or grinding it after it's hard for a more polished look. Or, very commonly, other finish materials like tile, stone, carpet, or wood treads are applied over the structural concrete base. Concrete stairs are known, as you said, for their exceptional durability, their inherent fire resistance, a major advantage in many building types, excellent sound dampening properties, they don't usually creak, and their ability to create a permanent, massive, monolithic appearance. They can be poured in place, cast in situ directly on the construction site, or sometimes manufactured as large precast units in a factory environment and then carefully lifted into position on site by cranes. This whole wet process, especially the curing time, often significantly impacts the overall project schedule.
So from a wet pour that needs time to cure, we move to steel stairs. That sounds like it might be a completely different approach, maybe more like assembly, perhaps faster on site.
Exactly right. Steel stair construction often involves a high degree of prefabrication and represents a fundamentally dry assembly process on site. Components like the main stringers, often steel channels or tubes, the individual treads, which might be steel pans designed to be filled later with a thin layer of concrete or solid checker plate for grip or open grading, and the handrail elements are precisely cut, drilled, bent, and often largely assembled into manageable sections within a specialized fabrication workshop environment off-site. These prefabricated sections or individual components are then transported to the construction site. There, they are typically lifted into place and assembled relatively quickly by skilled ironworkers or metal fabricators, usually using bolting or welding techniques to connect the pieces securely together according to the plans. This approach allows for very high dimensional accuracy because it's done in a controlled factory setting, and generally much more efficient construction on site, as much of the complex, time-consuming fabrication is done beforehand. Steel offers immense strength and rigidity relative to its weight, which allows for very slender profiles, visually light or open designs, and the ability to span longer distances without intermediate supports compared to wood or sometimes even concrete. This can create a very modern, industrial, or even delicate aesthetic. After assembly, steel stairs are usually finished to protect against corrosion and achieve the desired look. Common finishing processes include painting, powder coating, which provides a durable baked-on finish, or galvanizing, applying a protective zinc coating, especially for exterior stairs. Steel stairs can be left exposed to celebrate their structural form and industrial character, or they can be meticulously clad with other materials like wood treads, glass panels, or stone to integrate them seamlessly into a more refined interior design scheme. The potentially faster on-site assembly can significantly reduce disruption and shorten project timelines compared to, say, cast-in-place concrete.
It's truly fascinating how the material choice really dictates the entire construction process. Thinking about the different trades involved, the timelines, the level of on-site versus off-site work, and just the very nature of the work itself. A wooden stair almost feels like a piece of custom furniture being crafted with precision joinery. while concrete is almost like large-scale sculpting with a fluid material that needs time to set. And steel seems much more akin to precision engineering and mechanical assembly.
That's a very insightful way to summarize it. The wet process of concrete, with its reliance on formwork and curing times, involves a completely different set of skills, logistical considerations, and timeline impacts compared to the dry assembly of often prefabricated steel components. And the traditional craftsmanship, the joinery skills, and the finishing techniques required for intricate wooden stairs are distinct again from the industrial precision, welding expertise, and specialized equipment often needed for steel fabrication and erection. Each material truly demands specific expertise from the tradespeople, different types of equipment, and careful sequencing within the overall construction schedule. Understanding these fundamental differences is absolutely crucial for architects and builders for efficient project planning, accurate cost estimation, managing site logistics, and ultimately achieving a successful, well-built final product.
Okay, let's shift gears slightly now. Moving from steps to slopes, let's talk about ramps. They might seem simpler than stairs on the surface, just an inclined plane, right? But I'm guessing there's a lot more to their design than just making a sloped surface, especially when we think about accessibility. This feels like where universal design truly comes to the forefront.
Yes, this raises an incredibly important area. While seemingly straightforward in concept, ramps are absolutely crucial for achieving genuine universal design and ensuring equitable access for everyone within the built environment. They aren't just an alternative, they're often essential. They fundamentally change how people with diverse physical needs and abilities can interact with a space, moving beyond stairs as the only or even the primary option for vertical movement between levels. Their design might seem simple, but its impact is profound and requires careful consideration.
So, just to be clear, what's the core purpose and definition of a ramp, stripped down to its absolute essence?
Well, ramps are essentially defined as sloped pathways. They're used both inside and outside buildings specifically to provide accessible passage between different vertical levels. Their core purpose is really to offer a continuous, stable, and step-free alternative to stairs for people who cannot easily or safely navigate steps, or for moving items that cannot easily be carried up or down stairs.
And who are the main beneficiaries of ramps? We often instinctively think immediately of wheelchair users, and that's critical, of course, but their benefits seem to extend far, far beyond that single group.
Oh, absolutely. While ramps are undeniably crucial infrastructure for wheelchair users, enabling independent movement, their benefits extend dramatically further, potentially touching nearly everyone at some point in their lives. They provide an invaluable alternative to stairs for a huge range of people with temporary or permanent mobility issues. Think about someone using crutches after an injury, a person using a walker or a cane for stability, or individuals recovering from surgery for whom climbing steps might be painful or impossible. They also significantly aid parents navigating with prams or strollers. Anyone who's tried to lug a stroller upstairs knows the challenge. They help individuals pushing or pulling bicycles, shopping carts, delivery dollies, heavy luggage on wheels, or any other wheeled items. Expanding on this inclusivity even further, ramps profoundly improve the experience for many elderly persons who might find stairs increasingly challenging, tiring, or unsafe due to balance or strength issues. They're essential for delivery personnel moving heavy goods. Or frankly, they benefit anyone carrying heavy or awkward items that are far easier to push or pull up a gentle slope than to lift awkwardly up a series of steps. So it's really not just about meeting minimum legal compliance for wheelchair users, it's about making the built environment genuinely accessible, convenient, safe, and dignified for a truly diverse and dynamic population with varying needs and circumstances throughout their lives.
Okay, that's a great point about the breadth of benefit. Now, the crucial factor in ramp design has to be its slope or gradient, right? That seems like the single most important variable that determines if it works or not.
Absolutely. The gradient, sometimes called the slope or the steepness, these terms all refer to the same critical characteristic of a ramp. It's defined as the angular relationship between its rise, which is its total vertical height difference from bottom to top, and its horizontal projection or length, which is known as its run. This relationship is almost always expressed as a ratio for clarity and consistency. For example, the rise component might be set at a standard unit of 1. So a slope expressed as 1.211 means that for every single dimensional unit of height the ramp rises or falls, say 1 foot or 1 meter, the corresponding dimensional unit of horizontal length runs out by 20 units, so 20 feet or 20 meters. Understanding and controlling this precise ratio is absolutely critical because it directly impacts the amount of physical effort required to ascend or descend the ramp. This is especially true for manual wheelchair users who rely entirely on their own upper body strength to propel themselves uphill, and also for anyone pushing or pulling heavy loads. The steeper the slope, the exponentially harder it becomes.
So it sounds like a profound Goldilocks problem then. The slope has to be just right. If it's too steep, it's unmanageable or unsafe. But if it's too shallow, it becomes impractically long and eats up too much space.
Precisely. You've nailed the core tension in ramp design. It really is a Goldilocks problem. A ramp that has too steep a slope will prove incredibly difficult, if not impossible, for many intended users to navigate independently and safely. Imagine the sheer, often invisible, struggle of a manual wheelchair user trying to get up a ramp that's even slightly steeper than the standard. It's a monumental physical challenge that many able-bodied people might never even consider. And for those descending, a ramp that's too steep can easily lead to loss of control, potentially rolling backward unintentionally, or even tipping over, posing very serious safety risks. Conversely, whilst a ramp with a very shallow slope, say 1.3 or even gentler, might be incredibly easy to navigate, it can require an excessive amount of horizontal length to achieve the necessary vertical rise. This creates a significant practical implication. A very shallow slope takes up a disproportionate amount of valuable real estate or floor space. In dense urban environments, or within the tight confines of smaller existing buildings, dedicating potentially dozens of meters of length just for a single ramp can be a major, sometimes insurmountable, design challenge. It can force architects into complex solutions like switchbacks, ramps that turn back on themselves with landings, or other configurations, often increasing construction costs and architectural complexity significantly.
So this inherent tension between making it easy and safe enough to use for everyone, but also practical and efficient enough to actually build within real-world constraints. That's precisely why building codes are so strict and specific about maximum permissible slopes for accessible ramps. It's a carefully calibrated balance of human factors and unavoidable real-world constraints.
Exactly. That ongoing tension between steepness, which directly impacts safety, usability, and physical effort, and length, which impacts space requirements, cost, and overall building efficiency, is precisely why building codes and accessibility standards worldwide establish very strict maximum permissible slopes. For instance, a ratio of 1.1, meaning 1 unit of vertical rise for every 12 units of horizontal run, is a very common maximum slope allowed for accessible ramps in many regions, including under the ADA in the United States. Some codes might allow slightly steeper slopes, like 1.10 or even 1.8, but only for very short vertical rises, often with compensating factors like extra handrails. It's a precise balancing act, codified into law, to ensure both optimal usability for the widest possible range of people, including those with limited strength, and practical, efficient integration into a building's design. It aims to prevent hazards while still making the provision of ramped access feasible within real-world spatial, economic, and even aesthetic constraints. It's fundamentally about designing for humanity within the inescapable confines of gravity, physics, and real estate.
Wow. So what does this all mean when we pull back? We started this deep dive by just thinking about, walking up and down a set of stairs or maybe rolling up a ramp, things we do every single day, often without any conscious thought at all. But we've truly gone deep into the hidden complexities, the thought, the engineering, the human considerations packed into something so fundamental to our daily lives and our entire built environment.
Yeah, if we connect all these threads back to the bigger picture, it becomes abundantly clear that seemingly simple everyday elements like stairs and ramps are actually incredibly complex intersections. They bring together profound human factors: ergonomics, safety, accessibility, precise engineering and mathematical calculation, considered aesthetic principles and architectural expression, and critical, non-negotiable legal requirements from building codes and standards. They aren't just pathways to get from point A up to point B, they are truly profound statements about how we as a society and as designers approach and design for human movement, for safety, for inclusivity, and for dignity within the spaces we build and inhabit.
It's amazing. We've explored how different types of vertical connectors, stairs, ramps, escalators, elevators are strategically deployed based on things like building height and specific function. We uncovered that surprising insight into why shopping centers often prioritize escalators, almost turning the act of movement into a seamless part of the retail strategy itself. We've dissected those dual, sometimes conflicting objectives of stair design, the need to minimize physical strain while simultaneously reinforcing a building's unique character and style. And we look closely at how the choice of materials like warm wood, robust concrete, or sleek steel fundamentally shapes both the aesthetics and the very different construction methodologies required, each demanding different skills and impacting project timelines.
And we really did delve into the specifics, didn't we? Decoding that precise, almost anatomical vocabulary of stair components. We talked about everything from the critical spacing of balusters for child safety and the structural anchoring role of newels to the absolute necessity of consistent riser heights, the importance of comfortable tread depths, and even the subtle but vital ergonomic purpose of the nosing on each step. We saw how those stringent building codes govern seemingly everything, from the required height and graspability of a handrail to the safety limitations placed on those space-saving but potentially tricky winders. It really reveals the meticulous level of detail involved in attempting to make these everyday structures safe, compliant, and universally usable for as many people as possible.
And then there was the math. Actually walking through those precise computations for calculating the number of risers and treads, the landing size, the individual step dimensions based on floor height and available space. It showed us just how much precise engineering and careful planning goes into every single step you take. It's about transforming an abstract architectural plan into a tangible, safe, and functional pathway. And finally, we looked at ramps, seeing them not just as a simple alternative to stairs, but as a truly crucial component of achieving inclusivity in universal design. We came to understand how that critical gradient ratio, that slope, represents a delicate balance between ensuring usability for everyone, regardless of mobility, and managing the very real spatial and economic constraints inherent in building design.
It's genuinely a testament to an incredible amount of thoughtful design, rigorous engineering, painstaking calculation, and deep consideration for the human experience, all hidden in plain sight within structures we encounter constantly as we move through our daily lives.
So maybe the next time you encounter a set of stairs or find yourself using a ramp, pause for just a moment. Consider not just where it takes you geographically, but how thoughtfully, or perhaps sometimes how poorly, it was designed and built with you, the user, in mind. What subtle details can you now notice, having listened to this? Maybe the precisely consistent height of each riser, the comfortable depth of the tread under your foot, that tiny nosing easing your step, or the almost imperceptible but carefully calculated gradient of the ramp beneath your wheels or feet. How does its specific design, its shape, its material, its dimensions, influence your own experience of the space, or your ease and comfort of movement? And maybe even what does its very construction, whether in warm wood, solid concrete, or sleek steel, subtly reinforce or perhaps challenge about your assumptions regarding movement, access, and inclusivity in the world around you?